Hi all, welcome to MACM 101 tutorial 6. In this tutorial we'll cover sets and relations. Now since this is a new unit, it won't be related to predicates and quantifiers. The things we learn and discuss would be quite different. So without further ado, let's get started. We'll start on the first problem. It says investigate the truth or falsity of the following using three methods: Venn diagrams, laws of set theory, and providing that left side is a subset of right side, and vice versa. So the question given is A minus B union C is equal to A minus B intersection A minus C. So I've already created the Venn diagrams for you. Now for these diagrams, you are just creating three circles and all you need to do is shade the desired region. Now for the left hand side, we had the circles A, B, and C. So B union C would be addition of all the elements that are in B or C. And now A minus B union C would mean A and exclude all the elements that were in either B or C. So since this was A and this was B union C, removing this area from A gives us the desired result. So the area shaded in pink is our whole left hand side. Now for the right hand side, we had A minus B intersection A minus C. So this is A minus B and the red one is A minus C. Now you can see for the blue region, we have subtracted all the elements which were in B from A. All these we have removed. For the red area, which is A minus C, we have removed all the elements that were common in A and C. Now we are supposed to take the intersection of the blue and the red region. So this is the region that's common between both, and that's exactly what our left hand side looked like. That's how we can prove that these two are equivalent. Now to solve it using laws of set theory, we'll just start by defining what is A minus B, which is equal to A intersection B complement. Now we'll write down this question, which is A minus B union C. Now using the same rule, it can be written as A intersection B union C complement. Now this is using set difference definition. So now you use De Morgan's to open up the second bracket, which would give you A intersection B complement intersection C complement. Now we apply distributive law to open them up even further. That would give us A intersection B complement intersection A intersection C complement. Now again, this looks like the definition of set difference. So we can write it as A minus B intersection A minus C. And that's using set difference definition. So now for the third part, we are to prove left hand side is the subset of right hand side and right hand side is the subset of left hand side. So if A is a subset of B and B is a subset of A, that essentially means they both are equal. So all the elements that are in B are present in A, and all the elements that are in A are present in B. So it kind of makes sense. So now first we'll prove that left hand side is a subset of the right hand side. So here we'll just say that if A minus B intersection C is a null set, then the result basically holds true by the property of null set, because there are no elements in left hand side, meaning anything, it's all empty. So even your right hand side would be all empty and your result just basically holds true. That's why we will assume that A minus B intersection C is not empty. So let us assume that there's an element X which belongs to A minus B intersection C. Now, since it belongs to A minus B intersection C, it's safe to say that X belongs to A and X doesn't belong to B intersection C. Now, this implies X belongs to A and X either doesn't belong to B or it doesn't belong to C. So this leads us to two cases now. Our case one would be X doesn't belong to B, and the other case would be X doesn't belong to C. So for the first case, now if X doesn't belong to B, then X belongs to A minus B. And this means X belongs to A minus B union A minus C. Because if your X belongs to either of these, your whole equation is satisfied. So moving on to the case 2, X doesn't belong to C. So if X is not an element of C, then X belongs to A minus C. This means X belongs to A minus B union A minus C. Now, both the cases lead to the same conclusion, which is X belongs to A minus B union A minus C. Therefore, I can say that that A minus B intersection C is a subset of A minus B union A minus C. Now to prove that right hand side is a subset of left hand side, we'll start again by saying if A minus B union A minus C is an empty set, the result follows from the property of phi. So we are going to assume that A minus B union A minus C is not empty. Therefore, let there be an element X which belongs to A minus B union A minus C. Now, this takes us to two cases because there's a union. So first case is X belongs to A minus B. Now, this implies that X belongs to A and X doesn't belong to B. Now, since X doesn't belong to B, it implies X is not an element of B intersection C. Therefore, X belongs to A minus B intersection C. Now the other case is again pretty much similar. Let's say X is an element of A minus C. Now this implies X is in A and X is not in C. Since X is not an element of C, it further implies X doesn't belong to B intersection C. Therefore, X is an element of A minus B intersection C. Now, both the cases again lead to the same conclusion, which is X belongs to A minus B intersection C. This implies A minus B union A minus C is a subset of A minus B intersection C. Therefore, we proved left-hand side is a subset of right-hand side and vice versa. Now, moving on to the second question, it says use laws of set theory to establish the following. A intersection B union A complement intersection C and its whole negation is equal to A intersection B complement union A complement intersection C complement. Now, this is a bit tricky problem here, so we'll take it as we go. Now, this can be opened using De Morgan's. So first we'll take care of that negation. We'll write A intersection B complement intersection A complement intersection C's whole complement. Now we apply De Morgan's law again. This would be A complement union B complement intersection A complements complement union C complement. Now we use the involution law, or which we studied as double negation. It's quite similar. So it's A union C complement now. Now we use the distributive property to split them up again. This gives A complement union B complement intersection A union A complement union B complement intersection C complement. Now we apply distributive law once again in both of these statements, so which would be something like this. And now the first part, A complement intersection A, it's using the definition of complement. It's an empty set, therefore we'll be left with B complement intersection A union A complement intersection C complement union B complement intersection C complement. Now, this is as far we go from the left-hand side. Now we'll try to solve the right-hand side and try to meet somewhere in the middle. So let's start by writing what the right-hand side was. Now we'll start on the right-hand side by first using the distributive law. Now this can be written as A intersection B complement union A complement intersection with A intersection B complement union C complement. Now once we have this, we use the distributive law once more. Now this gives us A union A complement intersection A complement union B complement intersection with the right hand side again. Now A union A complement is a tautology, and tautology intersection with whatever is remaining gives us that portion. So now we have this. Now once again we'll use the distributive law, which will take us to A complement union B intersection A intersection B complement and A complement union B intersection C complement. Now here we apply the absorption law to reduce it to A intersection B complement, and whatever's on the right hand side we use the distributive law to open it up again. Now as you can see, this is equal to what we had achieved from the left hand side. That's how we prove they both are equal. So moving on to the next problem. Now it says using laws of set theory, simplify the following. Okay, the first one, it's A intersection B union A intersection B intersection C complement intersection D union A complement intersection B. So first I'll start off by using commutative law to shuffle them a bit, and now we'll use distributive law on the first two parts. It gives us A union A complement intersection B union the whole right hand side. Now the inverse law for A union A complement, it gives you the whole universe. Again, it's the same as writing a tautology. So it contains all the elements in the universe. So universe intersection B union A intersection B intersection C complement intersection D. So here using the identity law, because universe intersection with B will give you B. And again, we use the distributive law to open them up once more. And now, as you can see, there's one B union B. So using idempotent law, it leaves you with just a single B. And as you can see, there's a B and a union in all these elements. So you can use the absorption law, because in the union only one thing needs to be true. So using absorption law, it comes out to be B. The second part, it's A minus B union A intersection B. So first, using the definition of set difference, it's A intersection B complement. And now using the distributive law, I can write A intersection B complement union B. Again, using the inverse law, it gives me the whole universe. So A intersection universe using the identity law gives me A. And that's your solution. So question 4. Now it states let A, B, C, D be non-empty sets. So prove that A cross B is a subset of C cross D if and only if A is a subset of C and B is a subset of D. So we are given that A is a subset of C and B is a subset of D. We are supposed to prove that A cross B is a subset of C cross D. And here's the proof. We'll start off by assuming A comma B be an element of A cross B. Now, by the definition of Cartesian product, A belongs to the set A and the element B belongs to the set B. Okay. Now, we say if X is a subset of Y, then every element of X is in Y. So by the given statements, which we had of A is a subset of C and B is a subset of D, we also obtain that the element A belongs to the set C and the element B belongs to the set D. Again, by the definition of Cartesian product, A comma B is a subset of, A comma B belongs to C cross D. Therefore, we obtain that every element A comma B in A cross B is also present in C cross D. Therefore, A cross B is a subset of C cross D. Now, moving on to our fifth problem. It says, determine which of the following relations are on set A are reflexive, symmetric, transitive, and anti-symmetric. In the first one, we are given A is 1, 2, 3, and the relation is given as 1, 1, 1, 2, 2, 1, and 2, 2. So first we'll check for reflexive. Reflexive means in the relation A comma A should be present. So let's take the element 2, which is present in the set A. So in the relation, we should have 2 comma 2. That's there. But now for the element 3, A cross A would be 3 comma 3, and that's not present in the relation. Therefore, this relation is not reflexive. Now we check for symmetricity. So the symmetric property is if there is A comma B, then B comma A should also exist. Now to check whether the relation obeys the symmetric property, let's say we have the element 1 comma 2 which is present in R. So 2 comma 1 should also be there, which is for the other elements 1 comma 1 is there. So the reverse of that is also 1 comma 1, and that's also there. So for the last element, which is 2 comma 2, the reverse is still there. So for all the elements a comma b comma a exist, therefore the relation is symmetric. Now to check for transitive, it says if a comma b is present in the relation and b comma c is also there, therefore a comma c should also exist. Now let's take an example. Let's say 1 comma 2 and 2 comma 1 are there in the relation, gives 1 comma 1 which is also present. You could also give the example of 1 comma 2 and 2 comma 2. So this gives 1 comma 2 which is again present, therefore the relation is transitive. So you can check for all the elements. Now for anti-symmetric, it says if a comma b and b comma a exist in the relation, a should be equal to b. So for the example 1 comma 2 and 2 comma 1, we can say that 1 is not equal to 2, therefore it's not anti-symmetric. Now in the question we were also supposed to draw the graph and the matrix of the relation. So for drawing the graph, first we'll place all the points which are in our set, which is 1, 2, and 3. And all the relations which were there would be our means of connecting those points. So 1 comma 1 is a circle, 1 comma 2 is an arrow pointing from 1 to 2, and the same is 2 comma 1. 2 comma 2 is also a circle on itself. And since 3 didn't have any connectives with it, so it's left alone. Now for the metrics, it's the same. It's just we'll write 1 where we have a connection and write 0 where we don't. That's it. Moving on to the second problem, it says A is a set of all students in SFU where X comma Y and R means they have a height difference of 1 inch. Now for reflexive, again let X be an element in A. X R X, this relation will always be true. This relation holds for all X belongs to A because the height difference of X from the height of X is 0. Because we are talking about the same person actually. So that's why, since it satisfies, it's less than 1 inch, it is reflexive. Now for symmetric, again this relation holds true for all A comma B belonging to A, the set A, because height difference of B comma A is the same as that of A comma B. So if A comma B has a height difference of less than 1 inch, less than or equal to 1 inch, B comma A will also have the same height difference. Now to check for transitive, let's assume that there are 3 elements A, B, C which belong to the set A. Now A comma B belongs to R, B comma C also belongs to R, but we cannot say the same thing for A comma C, as now the height difference might be equal to 2 inches. If A comma B had a height difference of 1 inch, B and C had a height difference of 1 inch, A and C will have a height difference of 2 inches. Therefore, it's not transitive. And talking about anti-symmetric, again, let's assume A and B belong to the set A such that A comma B belongs to R and B comma A also belongs to R. So let me assume that A and B have a height difference of 1 inch. B and A will also have a height difference of 1 inch. Now, I cannot say A is equal to B as A and B have a height difference. So the only case where this would be true is when A and B do not have any height difference. But that's not the generalized definition which is asked in the question. Therefore, this is not anti-symmetric. Now moving on to the third part, it says A is a set of ordered pairs of real numbers. A is R cross R and x1, x2, y1, y2 is an element of the relation if and only if x1 equals y1 and x2 is less than equal to y2. Now, to check for reflexive, for each ordered pair x1, x2, x1, x2, comma, x1, x2 will belong to R because essentially x1 is equal to x1 and x2 is less than equal to x2. They both hold true, therefore this is reflexive. Now to talk about symmetric, if let's say x1, x2, comma, y1, y2 is an element of the relation R, then y1, y2, comma, x1, x2 should be equal to R. That's what the definition of symmetric means for all the elements belonging to A. Now, the first part which says x1 equals y1 and x2 less than equal to y2, this holds true, but talking about the reverse, y1 equals x1, but y2 is not equal to x2. I'm sorry, I forgot to put the not here, but it's not symmetric. So talking about transitive, now again assume 3 ordered pairs which belong to the set A such that x1, x2, y1, y2 is in the relation R, y1, y2, z1, z2 is in the relation R. Now we have x1 equals y1 and x2 is less than equal to y2. That's correct. y1 equals z1 and y2 is less than equal to z2. Now from the above two, it's safe to say that x1 equals z1 and x2 is less than equal to z2. Therefore, this set will also be there in the relation R, and hence it's transitive. Now to check for anti-symmetric, so let the element x1, x2, y1, y2 be in R. Now y1, y2, x1, x2 also need to be in R, but that's not possible. So because x2 was less than equal to y2, and in the reverse, it's not possible until and unless x2 is equal to y2. Therefore, this is not anti-symmetric. Now, the last problem wants us to find the equivalence classes and the number of equivalence classes. So for problem A, we are given with sets of all possible strings of 3 or 4 letters in the alphabet A, B, C, D, and Z is B, C, A, D, where X comma Y is in the relation if and only if they have the same first letter and the same third letter. So now the equivalence class of R, which contains BCAD, would also contain the string BCA, because all we care about is the first and the third letter. And since the strings can be 3 or 4 letters in length, therefore BCAD will also have BCA. So it consists of string BCA and the strings of 4 letters having B as the first letter and A as the third letter. Now, how do we decide on the number of equivalent classes? We know that the equivalence classes in this case are based on the first and the third alphabet. So all the distinct combinations of the first and third alphabets would give you different equivalent classes. Now, I would also say that the number of equivalence classes are different from the number of elements in each equivalent class. So here, your first element has 4 choices of A, B, C, D, and your third element also has 4 choices A, B, C, D. So there would be 4 square, meaning 16 different combinations that you can make. Therefore, there are 16 distinct equivalent classes of R. Now the second problem is a bit tricky here. It says A is the power set of 1, 2, 3, 4, 5 and Z is 1, 2, 3. And X, Y is in R only if X intersection 1, 3, 5 is equal to Y intersection 1, 3, 5. So the equivalence class containing 1, 2, 3 would be the set of such elements when you pick any 2 combinations and intersect with 1, 3, 5, they give you the same thing. So the only 4 combinations of such elements in A are 1, 3 and 1, 2, 3. We'll just wait for the video to catch up. It's 1, 3, 1, 2, 3. Now 1, 2, 3, 4 and 1, 3, 4. Now you pick any 2 elements from this and you intersect with 1, 3, 5, you will get the same result. That's why they are in one equivalence class. So if you say 1, 2, 3, 4 intersection with 1, 3, 5, that's 1, 3, and 1, 3 intersection with 1, 3, 5 is 1, 3. That's why they are equivalent. Now there are 8 different equivalence classes of the relation R, which would be the sets consisting of the power set A, then A union set 2, then A union 4, and A union 2 comma 4. And this would be for every A which is a subset of 1, 3, 5. And that's because the only elements left out from 1, 3, 5 are 2 and 4. So all possible combinations of 2 and 4 would be added to the subset of 1, 3, 5. And that concludes our tutorial. See you guys next week.